Okay, so this video will be about the JVM architecture. Now, if you go to the JVM spec, you'll notice that it's over 600 pages. So I'm just gonna try to give you guys a quick synopsis of the different components of the JVM model. So I'm just gonna start off by writing JVM model. Now, there are three, well, there's actually more than three, but you could conceptually break it down into three main parts. There's a class loader subsystem, there's the runtime data area, there's the execution engine, and then you also have other interfaces and method libraries to support native functionality, such as the native method interface or the JNI and the native method library. So I guess we'll start with the class loader subsystem. So maybe I should have drawn this ahead of time, but that's okay. Class loader subsystem. And this component is broken down into three additional parts: loading, linking, and initialization. Okay, so before I go further, I will give you a high-level overview of what the JVM does. So JVM stands for Java Virtual Machine. It's a crucial component of the Java platform that basically enables the execution of Java bytecode. The most important thing about it is that it provides a runtime environment for Java applications, and it also helps facilitate platform independence by abstracting away the underlying hardware and operating system. So, in particular, this loading function has three types of loaders. So there's a BCL, which we will call a bootstrap class loader. There's an ECL, which is an extension class loader. And there's an ACL, which is an application class loader. And then for linking, it's also broken down into three phases. We have a verify phase, a prepare phase, and a resolve phase. And then initialization just covers the initialization aspect of the entire system. So let's see. I tried to draw a square, but it came out squiggly. Let's see if I can do this straight. Okay, here is our class loader subsystem. And then I'm just going to draw boxes around it to try to make it look cleaner. Okay, so now that I've drawn it, I'll go into more detail as to what each component does. So loading covers the different class loaders you see here, and the class loader locates and reads the binary representation of a class file from the file system, network, or other sources. It then creates a corresponding class representation in the JVM. The linking component here, you see verification, preparation, and resolution. Verification ensures that the class file is valid and doesn't validate, I mean, not validate, I meant violate any security constraints. And preparation involves allocating memory for class variables and initializing their default values. And lastly, resolution resolves the symbolic references to other classes or methods. And initialization is when the class loader initializes the static variables and executes the static initialization blocks of the class. Excuse me. So now we'll cover another part called the runtime data area. So I'll just scroll down here and then I'll write runtime data area. And we can break this down into 5 parts: the method area. After I draw it, I think it'll be easier to explain. So that's what I'm going to do. Then there's the heap. Then there's the stack. And then each stack has each JVM thread has its own stack. So we can call it T1, T2, all the way to Tn. And then we'll draw boxes for the data in each thread. And lastly, we have the native method stack. Okay, so let me try to clean this up. Okay, here's our method area. Here's our heap. There's the stack. And here is the native method stack. Okay, so the runtime data area is a memory area used by the JVM during program execution. And it's divided into these components: the method area, which basically stores the class level data. So that would include the method bytecode, any fields and or method references, and static variables. The heap is where the runtime data area for the objects are allocated, get stored in. It's shared among all threads and managed by the JVM's garbage collector. And here we have the stack. Like I said earlier, each thread in the JVM has its own stack, which stores local variables, method parameters, and intermediate computation results. Instead of writing LC or MP or ICR for local variables, method parameters, or intermediate computation results, I just drew a box here containing that data. And if I didn't mention earlier, the stack also keeps track of all the method invocations used across the program. And now we have the native method stack, which is specific to native methods, which are written in languages other than Java. It handles the execution of native code and manages the method calls between Java and the native libraries. So now we covered the class loader subsystem. We covered the runtime data area. The last 2 parts are the execution engine and the native method interface. So we'll start with the execution engine. Just scroll down a bit. Okay. Execution engine. And then we can break this down into 3 parts: interpreter, which I'll explain in a second, JIT compiler. By the way, I forgive, I mean, not forgive me for my bad handwriting. Garbage collector. So here's the execution engine. Okay, I know this is definitely not readable, but this says garbage collection. Well, garbage collector right here. And here's the JIT compiler, and this says interpreter. So to go into more detail on what each one does, the interpreter reads the bytecode instructions line by line and executes them. It does provide platform independence, but it could be relatively slow. The JIT compiler, the JIT stands for just in time, and it dynamically analyzes the bytecode and translates the frequently executed sections, aka hotspots, into native machine code for efficient execution. It definitely improves it definitely improves performance, but it incurs an initial compilation overhead. And lastly, the garbage collector reclaims unused memory. So it helps free up memory that was previously allocated but not used by the program. So the next part is, and this is the last part too, the native method interface. Native method interface. And I will also write an ML. Actually, no, I'll just write it out. Native method library. Okay. So again, apologies for the bad handwriting. This says native method interface NMI, native method library NML. And native method interface is actually known as the JNI. I just said NMI for the purpose of this video, but it's really JNI, and it allows Java programs to call native methods that were written in other languages, such as C or C++. And it provides a way to bridge the gap between Java and platform-specific code, which allows you to directly interact with the system libraries or the hardware. And the native method library consists of precompiled binaries or shared libraries that contain native code. These libraries are platform specific, and they provide the implementation for native methods invoked by the Java virtual machine. So just to give you a high level overview of how this architecture looks now that I'm done. The JVM model comprises the class loader subsystem here, which loads, links, and initializes classes. The runtime data area, which includes the method area, the heap, the stack, and native method stack. The execution engine, which is responsible for interpreting or compiling bytecode, the native method interface, which facilitates interactions with native code, and the native method library, which contains platform-specific implementations for native methods. So ultimately, together, these components enable the JVM to execute Java programs efficiently and provide the platform independence that we all use today.